Let me ask you something. Did you know you're constantly walking around under the literal crushing weight of an ocean of air? It sounds crazy, but right now, at this very moment, there's a massive, invisible column of gas just pressing down on your shoulders. We rarely feel it, right? But this unseen pressure, it's actually the true architect behind every gentle breeze, every downpour, and every violent storm on Earth.
Welcome to this explainer. Today, we're going to completely decode the invisible engine that drives our planet's climate. We're diving into the chapter on atmospheric circulation and weather systems to demystify exactly how the nuts and bolts of our global weather operate. It's this incredibly fascinating system of balances, and imbalances really, and we're going to visualize exactly how the whole shebang works.
So, here's our agenda for today. We're looking at 1. The invisible weight of air. 2. Forces driving the wind. 3. Global atmospheric circulation. 4. Air masses and fronts. And finally, 5. Cyclones and violent storms. Let's get right into it.
Starting off with Section 1, the invisible weight of air. Atmospheric pressure is quite literally the weight of a column of air contained in a unit area. We measure this from mean sea level all the way up to the very top of the atmosphere. Down here at sea level, gravity pulls all this air densely together, which gives us an average atmospheric pressure of 1,013.2 millibars. You definitely don't feel it, but trust me, it is there, pushing in absolutely every direction. And the thing is, that pressure is highly dynamic. As you move up in elevation, say hiking up a mountain, the air gets thinner and the pressure drops. It's roughly 1 millibar for every 10 meters you climb in the lower atmosphere. But pressure doesn't just change vertically, it actually changes horizontally from place to place. And here's the crucial point. Nature absolutely hates an imbalance. Air is always going to move from areas of high pressure to areas of low pressure just to balance things out. That movement, that is exactly what we call wind.
Moving on to Section 2. Forces driving the wind.
So, there are 3 core forces that really dictate wind velocity and direction on our planet. Step 1 is the pressure gradient force. Think of this as the engine. It's what actually initiates the movement of air across those pressure differences we just talked about. Then, step 2 is the frictional force. The surface of the Earth isn't exactly smooth. Mountains, trees, buildings, they all drag and slow surface winds down, mostly in the first 1 to 3 kilometers of the atmosphere. And finally, step 3 is this really fascinating phenomenon called the Coriolis force. Because the Earth is constantly spinning on its axis, the wind doesn't just travel in a straight, simple line. The Coriolis force deflects the wind's path. It pushes it to the right in the northern hemisphere and to the left in the southern hemisphere. Now, the main thing you should take away from this is that this deflection is directly proportional to latitude. It's at its absolute strongest at the poles, and, this is critical, it is exactly 0 at the equator. Keep that little detail in your back pocket, because it perfectly explains why tropical cyclones literally cannot form at the equator.
So what happens high up in the atmosphere, say 2 to 3 kilometers above the surface, where there's basically no friction to slow things down? Well, the pressure gradient force gets perfectly balanced out by the Coriolis force. It's almost like a giant tug-of-war ending in a complete tie. The resulting wind just blows straight, parallel to the pressure lines. We call this geostrophic wind. Down near the surface, though, these forces actually cause air to spiral. Wind spirals inwards around a low-pressure center. We call that cyclonic circulation. And conversely, it spirals outwards from a high-pressure center, forming what's called anticyclonic circulation.
All right, Section 3, global atmospheric circulation. Here's the actual blueprint of Earth's heat engine. The equator receives intense solar heat, right? This causes warm air to rise, which creates a low-pressure zone. This air hits the top of the troposphere and travels toward the poles, eventually sinking around 30 degrees north and south to create these subtropical high-pressure zones. This forms a massive loop called the Hadley cell. Moving further toward the poles, we see the Ferrel cell in the mid-latitudes and the polar cell at the extreme ends. Together, these 3 massive atmospheric cells are acting like conveyor belts, transferring heat from the sweltering equator to the freezing poles, basically maintaining a habitable temperature for the entire planet. But you have to remember, these massive pressure belts aren't just frozen in place. If you compare global sea level pressure in January versus July, you'll see something interesting. Because the Earth is tilted, the region of maximum heating shifts throughout the year. And because of that, these global high and low pressure belts physically oscillate. They move southwards in the northern hemisphere's winter and then northwards in its summer. This shifting is exactly the mechanism that drives seasonal modifications, like those dramatic heavy monsoon seasons in Southeast Asia.
Let's look at Section 4, air masses and fronts.
Okay, so when air just sits over a vast, uniform area,
like a freezing, snowy continent or a super warm tropical ocean, it basically absorbs the temperature and humidity of that area. This creates what we call an air mass. But when two totally different air masses finally travel and meet, they don't just mix easily. It's not a smooth blend. The boundary zone where they clash is called a front. There are four main types you should know: cold fronts, warm fronts, stationary fronts, and occluded fronts. And these boundary lines, that is where some of the absolute most dramatic weather on Earth goes down.
When these boundaries crash into each other in the mid-latitudes, the results are honestly spectacular. When warm air from the south meets cold air from the north along the polar front, the pressure can drop, and that initiates a massive counterclockwise swirl of air. This creates an extratropical cyclone. Basically, you'll see a warm front gliding over cold air, which produces sequences of clouds and rain, followed really rapidly by a cold front aggressively pushing that warm air up, triggering towering cumulus clouds. These massive, sweeping systems are the culprits behind the abrupt, highly variable weather changes we see outside of the tropics.
And that brings us to Section 5, Cyclones and Violent Storms.
Now, it's super important to separate the extratropical cyclones we just talked about from tropical cyclones. Extratropical cyclones are these incredibly wide, sweeping systems that cover vast areas, feature clear warm and cold fronts, and they can form over land or sea. Tropical cyclones, however, they are a completely different beast. They originate strictly over warm tropical oceans, they do not have frontal systems, they cover a much smaller, tighter area, and their wind velocity is it's off the charts higher, making them infinitely more destructive.
So, what's the exact recipe to cook up a violent tropical cyclone, which, depending on where you live, you might call a hurricane, a typhoon, or a cyclone? Well, first, you need a huge source of energy. Sea surface temperatures have to be higher than 27 degrees Celsius. Second, you absolutely need the Coriolis force to make the whole thing spin, and remember earlier, that is exactly why they never, ever form right on the equator. You also need a pre-existing weak low-pressure area and upward divergence to physically pull that air upward.
If that specific recipe is met, you get this, a fully mature tropical cyclone. Look at the anatomy here, it's incredible. The energy that intensifies this beast comes entirely from condensation inside those towering clouds. The dead center of the storm is the eye, and bizarrely, it's a region of totally calm, subsiding air. But immediately surrounding it, that's the eye wall. This is where the storm reaches its absolute maximum fury. We're talking strong, spiraling air shooting up to the edge of the troposphere, bringing torrential rain and wind velocities as high as 250 kilometers per hour. Once this giant machine hits land, its oceanic fuel supply is essentially cut off, and it slowly dissipates, but usually not before causing massive destruction.
And of course, we can't talk about extreme weather without mentioning the localized chaos of thunderstorms and tornadoes. While tropical cyclones are massive and can last for days, thunderstorms and tornadoes are severe, short-duration events. On really moist, hot days, intense convection causes warm air to rapidly updraft, growing these massive cumulonimbus clouds. When those updrafts become extreme, they can actually spawn spiraling descents of air with a remarkably low-pressure center, a tornado. And as we know, they're capable of absolute massive destruction in just a matter of minutes.
Ultimately, what you should take away from this explainer is encapsulated perfectly in this thought. All of these storms, from the gentlest sea breeze to a roaring, destructive hurricane, are really just the manifestation of the atmosphere adjusting to an uneven distribution of solar energy across the globe. Through all the chaos, the potential and heat energy are converted into kinetic energy, basically blowing themselves out until the restless atmosphere once again returns to its stable state. So the next time you step outside and feel the wind on your face, ask yourself, what vast, invisible forces thousands of miles away just initiated that breeze? Thanks so much for joining me on this explainer, and keep looking up.